So working out whether a redox reaction is taking place or not is sometimes quite hard to do. But a useful tool that allows us to do this is the oxidation number, or the oxidation state, as it is sometimes called. A reaction we have previously observed is a combination of zinc with copper sulfate. And in this particular reaction, it's quite easy to work out if it's being oxidized or not. We can quite simply look at charge. Zinc is neutral to begin with. It's ending up as +2, so we know it's lost some electrons. Copper is starting off as +2, or 2 plus, and ending up as 0, so we know it has gained some electrons. Basically, what we've just done is assign oxidation numbers. So the important thing to understand here is that oxidation number is just another way of approaching charge. The benefit, though, of oxidation number is that we can use this technique for other substances as well, not just ions, but covalent substances as well. When we get into using oxidation numbers, there are a few simple rules we need to follow. We're going to go through these rules and then apply them to some examples. Now, as we go through these rules, I encourage you to write them down somewhere. But the first and most important of these rules is the fact that when you have an ion, the oxidation number is quite simply its charge. So an ion like iron 3 plus, its oxidation number will be +3. You'll notice a key difference here in that we write oxidation number as the sign and then the number, so +3, whereas charge is 3 plus. And the reason we do it this way is to distinguish between the two. So next up, when we're dealing with polyatomic ions, when you add up all the oxidation numbers of the component elements, they should add up to the overall charge. So for example, if you look at sulfate, SO42-, if you add the oxidation number of 1 sulfur and 4 oxygens all together, they should add up to -2. The third rule is that when you have things in their elementary form, so magnesium or Cl2 or even S8, their oxidation numbers, the oxidation number of each individual atom is 0. And finally, if you have compounds, whether they're ionic or covalent, like NaCl or H2O, their oxidation numbers, the oxidation numbers of the component atoms, should add up to give you 0. So now moving on to some slightly more specific rules. When you look at metals, particularly group 1 and 2 metals, you can normally work out their oxidation number when they're an ion or in a compound by looking at their charge. So group 1 and 2 metals normally have an oxidation number of +1 and +2 respectively. Examples of this are sodium and calcium ions. So if sodium, for example, was in sodium chloride, NaCl, it would be +1. Calcium, if it was calcium oxide, it would be +2. The next rule is a little bit of a confusing one, and that's for electronegative elements, such as halogens. When they're in compound, they are normally negative. Their oxidation number is normally -1 or -2, or depends what it is, unless the other atom they're bound to is more electronegative. So for example, if fluorine and chlorine were bonded together, fluorine would be negative. The chlorine would have no choice but to be positive. This gets a bit tricky, but it's not a very commonly used rule. Your next rule is probably your most useful rule, and that's the hydrogen rule. Generally, hydrogen, when in compound, such as H2O, it is +1. The only exceptions to this are in rare cases when hydrogen bonds to metals or metalloids. But normally when you see hydrogen, each hydrogen is +1. So in H2O, the two hydrogens together are +1 each, +2 overall. And our last rule, also of equal importance, is the oxygen rule. And normally oxygen, when you see it in a compound, such as CO2, it's normally -2. The only exceptions to this are when you find it in peroxides or when you find it bound to fluorine, because fluorine is a little bit more electronegative. What we're going to do now is apply all 8 of these rules to specific examples. You might also notice a few overlaps. You don't actually need all 8 often. Sometimes there are double ups, but you use whichever rules you need to find the oxidation number of specific examples. Okay, so we've got 6 questions here, and each of them want us to find the oxidation number of nitrogen. Now, there are multiple ways you can approach these questions. You will have to use some of those rules, but the way you set up your question can be in one of 2 ways. You can do it a little bit intuitively. For starters, hydrogen. We know that hydrogen is normally +1. And if there are 3 lots of hydrogen, all up, that's plus 3. Which means, to balance it out, the nitrogen in this case has got to be minus 3. The other way you can do this is to set it up using some algebra and write it this way. So you can say that nitrogen, whatever its oxidation number is, plus 3 lots of hydrogen should add up to give you 0. Remember, when you have compounds, their oxidation numbers should add up to give you 0, because overall the compound is neutral. And then you replace the hydrogen there with plus 1 using the hydrogen rule, and you rearrange this, which will give you n equals negative 3. Do whichever of these two approaches you're more comfortable with. I would say probably try both for these 6 examples and see which one works better for you, but try and stick to one method and make sure it's accurate. So next we have NO2, and again, if we set it up mathematically, we'll get N plus 2 lots of oxygen gives you an overall 0, right? And then you replace oxygen with its oxidation number. Remember, the oxygen rule is that oxygen is normally minus 2, unless it's in a peroxide or with fluorine, and none of that's happening here. So that gives you N minus 4 equals 0, so N has got to be plus 4. You can also do it intuitively the other way I said, but you should get the same answer. Question 3 involves a metal, in this case sodium. It's 3 lots of sodium plus nitrogen should give you 0. Again, compounds add up to 0. And if we use the rule about group 1 and 2 metals, we know that group 1 and 2 metals are normally plus 1 or plus 2. Sodium is in group 1, so it is plus 1. Adding together with nitrogen should give you a 0. So 3 plus N is 0. N has got to be minus 3. So the oxidation number of nitrogen in this case is minus 3. Moving on, lithium nitrate. This one's a little bit trickier. There are actually a few ways to approach this. The way I'm going to approach it is by ditching the lithium and just looking at nitrate. Remember, polyatomic ions, their oxidation number should add up to charge, and the charge of a nitrate is minus 1. So in other words, whatever nitrogen is plus 3 lots of oxygens should give me minus 1. So I'm going to sub my oxygens in again. Remember, oxygen is minus 2. That oxygen rule is going to be one of your favorite rules by the end of this, hopefully. So what does this give you? N will therefore give you plus 5. Then finally you have N2O4. N2O4 here, 2 nitrogens plus 4 oxygens should give you 0. And then 2 nitrogens plus, remember, 4 oxygens, so that's 4 times minus 2, which should give you 2N equals 8. So N equals 4. When you find oxidation numbers, you have to find it for each individual atom. So not overall, all of the nitrogens together, but each individual nitrogen. And each individual nitrogen here is plus 4. And then finally, N2. This one is the hardest or the easiest of the lot, depending on how you look at it. Remember the first rule, or the third rule, whichever one it was, that free elements by themselves, their oxidation number is 0. So in this case, the oxidation number is 0. Before moving any further, I would say pause the video and do all the questions you can on page 75 of your activity books and get used to using these rules. Once you're done, come back and we will look at equations and oxidation numbers. So we're going to use oxidation numbers in equations now. So here we've got a magnesium reaction reacting with hydrochloric acid. Go ahead and find the oxidation numbers of each individual atom in this species. The key thing to note is when you're doing oxidation numbers, ignore coefficients. The numbers, the little numbers, the subscripts matter, but the coefficients, leave them out. Ignore them. They play a role later on. If you've done it correctly, you should get oxidation numbers of 0 for magnesium, plus 1 for hydrogen, minus 1 for chlorine, plus 2 for magnesium there, minus 1 for each chlorine over there, and 0 for the hydrogen down the end. over there. Now that tells you something. That tells you that there are a few elements which are changing. In this case, the ones that are changing are your magnesium and your hydrogen. Because your magnesium and your hydrogen are changing, the redox reaction here is primarily involving magnesium. So magnesium changes from 0 to +2, and this is a increase in oxidation number, and when oxidation number goes up, this is considered to be an oxidation. So when oxidation number increases, you've got an oxidation reaction. On the flip side, hydrogen changes from +1 to 0, and because of that, hydrogen is said to be reduced. Hydrogen is undergoing reduction. So magnesium is being oxidized, hydrogen is being reduced. You could take this a step further and also say that magnesium is the reducing agent. Because magnesium is getting oxidized, it's enabling hydrogen to get reduced. So magnesium is the reducing agent. Hydrogen is the oxidizing agent. It is enabling magnesium to get oxidized. We could also trace how many electrons are being transferred over here. If you're doing that, you need your coefficients to play a role. Magnesium is going from 0 to +2, meaning it's losing 2 electrons. Hydrogen is going from +1 to 0. It looks like it's gaining 1 electron, but remember that there's that coefficient of 2 in front of it, so that could tell you that it's 2 electrons, 2 lots of hydrogen, so 1 electron each. But for the moment, we're only going to be using oxidation numbers to work out what is being oxidized and what's being reduced. The next equation we're going to do looks like this. It's a acid-base reaction, sodium hydroxide plus hydrochloric acid. What we are going to do, pause the video and try and work this out for yourself, and then we're going to discuss it in a second. So basically what happens here is sodium is +1 over there to begin with. It's also +1 over here. We'll do these one substance by substance. Sodium is +1, oxygen in sodium hydroxide is -2, hydrogen is +1. Again, follow all those rules and do all those steps, but when you work out their oxidation number, that's what you should get. Hydrogen is +1, chlorine is -1, sodium over there is +1, chlorine is -1, hydrogen is +1, each hydrogen is +1, so +2 overall, -2 for the oxygen. And what you'll notice if you look at all these oxidation numbers is that nothing changes. Oxygen is -2 to begin with, it ends up as -2. Same for hydrogen, same for chlorine, same for sodium. So no change in ox number, therefore not a redox reaction. Not everything happens to be a redox reaction. Sometimes you have reactions that are not. Just quite simply, they're not redox reactions. And this is one of those examples. Next up, we have this reaction, zinc plus copper sulfate. It's the reaction that kicked us all off at the start. Try to pause the video and do the oxidation numbers. If you've done them correctly, you should get zinc as 0, copper as +2, sulfur as +6, oxygen as -2. Now it's also important to note that you don't actually need to do all of these elements in sulfate, I should say. If you want to, you can just do the copper. If you can see that sulfate's not really changing much, you can get away with just ignoring it and focusing more on the copper it's bound to. But anyway, moving on, zinc +2, sulfate again +6 for sulfur, and then -2 for oxygen, and then copper is 0, which shows you that zinc is changing from 0 to +2, and therefore that is oxidation. Copper, on the other hand, is changing from +2 to 0, and that is reduction. Our final example is a bit of a tricky one. Pause the video and have a go once again. If you've worked it out correctly, your sodium should have an oxidation number of +1, oxygen should be -2, and hydrogen should be +1. Now remember, you ignore the coefficients, that 2 in front of NaOH, you can kind of ditch it if you're working out oxidation numbers. Chlorine, 0. Sodium, +1. Chlorine, -1. Sodium, +1. And then we get to chlorine and oxygen here. This is a compound called hypochlorite. Now, in this case, oxygen is going to be -2 because it's more electronegative, so it wins that battle. And chlorine has no choice but to be +1. And then hydrogen and oxygen are +1 and -2 respectively. So the weird thing here is chlorine is changing from 0 to -1 in NaCl. Chlorine is also changing from 0 to +1 in NaClO. So in other words, chlorine is both being oxidized and reduced. So we can say that chlorine, when it becomes NaCl, that is a reduction. But when it becomes sodium hypochlorite, that's an oxidation. This is possible. It can happen in some cases. All right, if you want to do more practice, there are more practice questions on page 77 and 78 of your activity books. Please do as much of this as you can. Thanks for listening.